But hopefully we'll have pizza shortly. But you should all come out, hear Klaus. The talk is awesome. Klaus is great. If you have interest in Crate, I'm sure he'd be happy. He's going to get here the night before, and he'll be here till, I think, the afternoon. So if anybody wants to talk to him about applications of Crate, I'm sure he'd be happy to do that. And I can help arrange that if you want to reach out. So.
Any other announcements? Anybody got a meetup coming up they want to give a shout out to? Maybe? No? When's the next Andrew? When's the next conference? Dev conference? Isn't that coming up? Yeah. There you go. They're upstairs. They're talking about it right now. So that's happening. All right, so no more stalling. You know, hey, maybe pizza shows up and we get to feed you, hopefully. In which case, we'll figure that out once we get there.
It'll be fresh.
Yeah, super fresh. Anyway, without further ado, let's give Anna a warm round of applause. She had some traffic trouble coming up today, so yeah, let's get her plugged in here.
Sorry I'm late.
Mike.
Coming up from Dalton, and all of a sudden Google says, there's an accident on 26. Would you like to divert to 41?
Yes, please.
I need yeah. All right.
Cable on the way. Today is how many? Is it anybody's first time today? Anybody? You? Welcome. Welcome. Usually pizza's here. Promise you that. That's usually a given. So next time you come, we'll be for sure feeding you. That's normally a thing for CHADEV. Thanks to these fine folks, among others, they foot the bill for that every week. So our operating budget is not small, trying to feed 40 folks every week on average, or 50 or whatever it is now. So, yeah.
Oh, it is there.
Okay. So,
I'm sorry.
yay. Either way. Okay.
All right.
Just wants to point everywhere. There you
How's
go.
this? That's better. Okay.
All right.
So,
They'll switch it
there we go.
momentarily.
Drum roll, please.
Everyone give Ann another round of applause for putting up for our beautiful chaos here.
So how about that parking? I did plug in. Yeah?
Oh. I have one of these.
I'm going to have...
Let me go grab a different adapter. I've actually got one.
Okay. And he said I had a hard stop at 50 minutes, so I hope this doesn't count against my time.
We can play with that time a little bit, I think, today. So probably what we'll end up doing, since we're running a few minutes behind, I know some folks need to be back at like 1. So feel free to duck out when you need to. For the folks that can stay around, do so. Do you have like a full 50-minute talk?
Well, I timed it at 40 and then 10
Yeah.
questions, so
Okay.
hopefully we're okay.
Cool. So
and-
we'll likely just do 40 minutes, and then folks that can stick around for the question can.
Okay. So I'll just go ahead and yay! Dual screens. Okay. Where's my mouse? Oh, my mouse is not plugged in anymore. That would be why. go. Okay. So, hi, thank you for having me. My name is Ann Campbell, and I'm a product manager at SonarSource, which is the company behind SonarQube, SonarLint, and SonarSource.com. I won't spend very much time flogging those products at all. I will use them in my demonstration some today, so you'll see how fabulous they are, but that's it. SonarSource in December published the cognitive complexity metric. It was published as a blog post and a white paper. I'm the principal author, but I got considerable help from my colleagues Freddie Mallet and Jean-Christophe Collet. As you might have guessed, they're French. And I'm here today to talk about cognitive complexity, the new metric. I have a monitor up there, great. Right in the light. So the agenda for today is to talk first about why I thought the world needed yet another metric, then to explain what cognitive complexity is, how it works, and then to look at some refactoring examples. So I'll dive right in. First, the question why I thought the world needed yet another code metric. There are lots and lots of code metrics out there, and this garbage on the page is just a small sampling of the metrics that are available. Now, I've named this metric cognitive complexity, and the go-to metric for most people for complexity is cyclomatic complexity. Cyclomatic complexity was put out by Thomas McCabe in 1976. It was formulated in a Fortran environment, but the principles all go across to other programming languages because logic is logic. And it was developed with an intent to measure both testability and maintainability. To do this, it uses a mathematical model to count the number of paths through a piece of code. And while it measures testability very precisely, it tells you exactly the minimum number of test cases you need to test any module, his word, or method. It does not accurately measure maintainability, or as I call it, understandability, and I'll show you why. This is a method which gets a score of 4 for cyclomatic complexity, and that's because there are 4 paths through the code. That is the 4 cases in the switch statement. But I think anyone who's dealt with cyclomatic complexity knows that when your method consists entirely of a single large switch statement, let's say 20 cases, you get a cyclomatic complexity of 20, and the tools will tell you, hey, this needs to be refactored because it's too hard to deal with. And okay, yes, you need 20 test cases to fully test it, but it's not all that hard to understand, right? So cyclomatic complexity is not adequately measuring the understandability of a method that contains just a switch case. And at the same time, this method also gets a cyclomatic complexity score of 4 because there are 4 paths through the code. But this code is a lot harder to understand. I've got 2 4s, one nested inside the other, a nested switch, a break to a label. I'll be honest with you, it took me a good 7-10 minutes to fully understand what this method was doing the first time I looked at it. But unfortunately, cyclomatic complexity gives this an equal score with my simple switch state method. And that's why I thought the world needed yet another metric. So this is where we come to cognitive complexity. And as I said, cyclomatic complexity uses a mathematical model to measure the paths through the code. But I think it demonstrates that for understandability, which is a human process, a mathematical model is inadequate. So in formulating cognitive complexity, I've departed from mathematical models, and we're using human judgment here instead. Now, a lot of the basis for this was, what does cyclomatic complexity do? Let's see if that's adequate. So some of this will be a little bit familiar to you as I go forward if you're already familiar with cyclomatic complexity. Cognitive complexity has 2 motivations and 3 guiding principles. Very quickly, the first motivation is to measure understandability. Duh. The second motivation is to incent good code. In all my time working with SonarQube, what I've learned at a very deep level is that if someone measures it, someone else is going to try and improve the score. And whether or not that change makes sense for the code, whether or not that change makes the code more readable, if you increment for it, someone somewhere is going to take that increment out of the code, maybe making the code harder to read. So the first motivation here is to incent good code, which leads directly to the first guiding principle, which is to ignore structures that make code more readable. A good example of this is an early return. Now, there are some purists who will say that early returns are evil, but I've seen many, many, many cases where an early return made the code more understandable. So, in adherence to this guiding principle, there's no increment for an early return. Similarly, there's no increment for a method structure. Cyclomatic complexity increments just for having a method. Cognitive complexity does not. Why? Because if I have a method with 100 lines, and I excerpt 20 of those lines into a separate method, in the main method, I can shorthand that 20 lines into one hopefully evocatively named call, and I've made the code easier to read, which is why there's no increment in cognitive complexity for the method structure itself. This has interesting implications. Many, many studies have shown that cyclomatic complexity at a level above the method really corresponds to lines of code. Because we don't have this basic increment for the method itself, things like domain classes can have a cognitive complexity of 0. So you can, at the higher levels, start to really look at the metrics to understand where in your program the complexity is concentrated. I'm not going to look at methods today, but because we're refactoring, but that's one of the interesting implications. Another thing we ignore is null coalescing operators. Now, we don't have these in all languages. You have them in C#, PHP, some of the other languages. And what a null coalescing operator allows you to do is shown the long way. Yeah, I noticed it gets louder when I look that way. So should I take this one off?
Just
Okay. Okay. So what a null coalescing operator allows you to do is shown the long way on the left, which is, set your default to null, test the other object. If it's not null, set it to part of the object, dereference the object. And once you understand the syntax on the right, the null coalescing operator, that's allowed me to shorthand those 4 lines of code into one. So even though there's some structural logic there in that null coalescing operator, because it makes code easier to read, we're going to ignore it. Okay? The next guiding principle is to increment for breaks in the flow. So what I mean by that is, ideally, you can start at the top of a method and read straight down in a single fluid motion. But when we hit things like loops, like ifs, things that you have to consider as a branch in the control flow, then that takes more effort to process mentally. And so we reflect that in cognitive complexity by incrementing for that. Specifically, we're going to increment for if, else for loops, sequences of logical operators. And if you're familiar with cyclomatic complexity, every logical operator gets an increment. But the fact is that A is not much harder to understand than, well, it is about as hard to understand as A and B and C. Same for A or B versus A or B or C or D. That's about equal because you kind of paid the price when you hit the first operator, and then you just add on for the others. So we're not going to increment for every logical operator, only for sequences of operators. And that'll make more sense as we look at some code. We're also going to increment for a switch. Now, a switch in cyclomatic complexity is my bad example, right, of how cyclomatic complexity works. In cognitive complexity, because switches are easy, we only increment once for the whole switch, no matter how many cases it has. And this, again, is where human judgment trumps the mathematical model when we're trying to understand how hard something is to understand. Jumps to labels, right? So something that makes you go backwards in the code flow, we increment for that. A catch, that's a bifurcation in the logic just as much as an if. And recursion. Recursion is a meta loop, so that would be reason enough to increment for it. But even a lot of seasoned programmers blanch at the thought of dealing with recursion. So recursion, a direct recursion cycle, so a method calls itself, that gets an increment of 1. If you've got an indirect recursion, then each method in the cycle gets a +1. Finally, we increment for nesting. I think it's intuitively obvious that if I have a sequence of 5 ifs in a row, that's going to be easier to understand than if I have those same 5 ifs successively nested. Right? And so because nesting one structure inside the other increases the mental load, we're going to increment for that nesting level. So specifically, the things that get a nesting increment are ifs and ternaries. We don't increment the nesting count for else's and else ifs because those are tied to that initial if where we've already paid the nesting penalty mentally. We increment for switches when they're nested, for loops, for catches. And as a special case, we don't increment for nested methods or for nested lambdas because we don't increment for the method structure. But they do increase the nesting level. So if I have a method and inside that a lambda and inside that an if, that if is a +1 for the if and then +1 for also being nested inside the lambda. This will make more sense once we start looking at code. So I've outlined now how cognitive complexity works. Let's go back to our 2 example methods where we see that cognitive complexity on sum of primes, we get a 7 because we've got +1 for the first 4, +2 for the second 4. That's 1 for the 4 itself and 1 for the nesting. We've got +3 on the if. That's 1 for the if, 2 for the nesting. We've got a break to a label, so that's +1 there. That doesn't get a nesting increment. And that gives me a total of 7 for sum of primes versus get words, which consists only of a switch. That's a total of 1. So now we've got relative complexity scores that make a lot more sense. Without looking at the methods to know which method is going to be harder to maintain. All right, so I promised refactoring in the abstract for this talk, so now I'm going to get to it. Find my mouse again. All right, so I'm in IntelliJ. I don't know how many of you use that. And I'm using the SonarLint plugin. The SonarLint plugin runs, right now we're using the Sonar Java analyzer, which is the same analyzer that SonarQube itself uses. And I can use this standalone or connected to a server. Right now I've got this particular project in my IDE connected to a local host instance of SonarQube that's running only one rule. Typically, if I were to look at the list of issues, I ran through this talk right before I came up here, and I forgot to undo my refactoring. So let me just revert state here for a second. So you've just seen one of the neat things that SonarLint does, which is analyze your code as you type and raise issues for you there in the IDE, so you know what's going on before you check it in. So normally you would probably see more than one issue in a file. As I said, I've got this particular project connected to a local host instance that's only running one rule, which is the cognitive complexity rule for Java. So that's why we're only seeing one issue. And here in my issues pane is my listing. I'm going to double click on it to be taken to the issue location. And here in the bottom right, I can see details on the rule that was broken if I want, and I can see any secondary issue locations that are relevant. So let's just step through this really quick and see where our increments are. Here on line 159, I've got a +1 for the if, and then I jump to +3 here on line 162 for this ternary operator. And so I'm +3, 1 for the ternary, and 2 for nesting. And you may be wondering, how did we get to a level of 2 already? Well, we've got this if that we're nested inside of, and we've got a lambda. So the lambda, there was no increment for the lambda itself because it's a method-like structure. There's no increment for methods. But it did increase the nesting level, which is why we jumped to +3 for this nested if. And then the nesting just gets worse from there. We've got a +4 for this if, 1 for the if, 3 for the nesting, +5, that's 4 points of nesting, +1 for the else because we've already paid the nesting penalty mentally on the if. Here's another else, +1 for that, +5 for this if, 1 for the if, 4 for nesting, 1 for the else, and then we're done. So when I'm refactoring with cognitive complexity, the first thing I look at is where the points are coming from. And in this method, the points are coming mostly from the nesting. We don't have a lot of logic here. We don't have a lot of if statements, a lot of for loops. It's the nesting itself that's the problem. And you know, the go-to method for refactoring some of this is to extract into a separate method. That's not always possible, though, because sometimes we have early returns, and we don't have any early returns in this. So that would definitely be a possibility to extract the contents of this. But then we've got a lambda that's calling a method. Now, anytime you've got a lambda with this much going on in it, that's probably questionable, but I'm going to call this a style issue and move on. But there are a couple things we can do here to eliminate some complexity. Now, we're starting out at a complexity in this method of 22. We've set the default threshold to 15. We did that through internal testing and feedback. 15 seemed like about the right number. So we need to drop 7 points. That sound is really, the volume is really up and down, and I'm sorry about that. So there are a couple things we can do here. The first thing I notice is that this if is the only thing inside the else. So if I move that up, shoot. This is a little weird to have the keyboard here and the screen here. So let's just pretend that I outdented that. That drops me to 17. And why did that one little change drop so dramatically? Because I lost a lot of nesting points when I did that, because there's no nesting increment for the else if. And so I dropped all the nesting points on that if. Which, you know, and this is not just an academic exercise. This is not just a game of, you know, how to get rid of the points. I think this change makes the code easier to read. Other thing that we can do, if we want to meet the threshold, we've got to find 2 more points, right? So look at this. I've got an if at the top. If my condition is met, then I do all of this. So what if I flip this condition? Now we see that from 17, my issue goes away. All right. As an exercise, let's double check what the total complexity is. I've got, whoops, got 1 for the if, 4, 5, 6, oh, I forgot this one, 7 for our ternary, 10 for my sequence of 1 logical operator, 11 for the else. So with 2 small changes, I've gone from 22 down to, what did I say, 12? And at the same time, again, this is not just an academic exercise. If I had been able to correct the indenting, I think that demonstrably makes the code easier to read. Another example. And I didn't mention this, I think, but this is the code of the Sonar Java analyzer itself. So this is sort of a recursive demonstration. This method, I'm at a total of 24 versus the 15 allowed. And if I look down here in the secondary locations pane, I see that I add up for nesting here. So I'm going to look first at this switch. And just right off the bat, anytime I see logic inside a case, my first thought is that needs to be in a separate method. Just because my philosophy is that's the way switches ought to work. But we've got early returns in this switch. And because of those early returns, we cannot factor this out into a separate method. Now we've got these nested ifs. So, it would be possible to save a couple points of complexity by pushing that off into a separate method, but I don't think it's worth it. That's really just playing the game for the sake of playing the game. It doesn't do a lot to move 3 lines out. But we're still over the threshold, and let's see if we can get under the threshold because, again, this is going to help maintainers, going to help posterity here. And so I look at this other chunk of code here, and I don't have any early returns, so this is definitely a candidate for moving off into another method, but let's see first if there's anything else we can do here. I can't combine these ifs because I've got this else. Now I could repeat the condition, but again, I don't think that gets us very much. There's really nothing else I can do in the else. So if I just move this off into a separate method, and I'm going to every branch in this block does this in queue new program points, so that's what I'm going to name my new method. And now my issue goes away. And I think this primary method, the one that we started with, arguably, I've got a switch that steps through and handles various cases. And then when all of that's done, I'm going to enqueue some new program points. So even if you don't know this code, I think that makes this easier to understand. Now, because I think it would be tedious for you guys to very painfully watch me refactor other pieces of code, I'm going to switch back to the browser and I'm going to use some code that's in some public instances of SonarQube.com. of SonarQube. So talk about in each. So here's my first example. Okay, this method is at 17. And by the way, I'm going to be on a couple different instances of SonarQube. One of them is SonarQube.com, which is open to the public. Anyone can analyze an open source project for free. There are instructions to get you started on the front page. I'm also going to be looking at next.sonarcube.com, which is where we dog food the changes that are coming in future versions. And I'll also be looking, I think, at Peach, which is where we internally test rule changes. You guys can't get to that one. But it's real easy for me to find examples. So we're starting out on sonarcube.com. This is an open source project, and this method has a cognitive complexity of 17. You know, we only need to get 2 points here. If I look at where the points are coming from, so here on the right are my secondary issue locations. This is telling me where the increments are. And I've got some points here from nesting. I think that's a +4. So, you know, normally the nesting is going to be the first target. Because if you can get rid of the nesting, that's going to help. Getting rid of the nesting is one of the first things to look at doing. And the thing that I notice here is that I've got this if, and if my condition is true, all of this, I'm going to return fair booked. So classic case for an early return. That drops the nesting level of everything inside by 1 point. I counted it up earlier. I think we saved 7 points on this, well below the threshold. So 2 points, that was sort of a trivial example. Let's make this a little harder. Here we've got 27 versus the 15 allowed. And if I look at where the points are, got a little bit of nesting here early in the method. Most of it comes, you know, the structure's not very deep. It's fairly shallow. And extract this to another method because of all the early returns. So you might think we're stuck, but there is the part where we increment for each if, and we assess a nesting penalty on each if. So if I come down to this section where I've got all these nested ifs, now as a maintainer, I come and I look at this, and just at a glance, I think, okay, I need to understand every single one of these ifs. And then you start reading it, and you see that, oh, if I execute the code in the first if block, I've got an early return, so I'll never get to the second one. If I get to the code in the second if block, I have an early return, so I'll never get to the third one. This is the same characteristic that an if-else-if chain has, right? You're only going to execute one of the blocks. So if we chain these together as if, else if, else if, else if, one, that's immediately clearer to maintainers what's going on. And not consequently, we drop the nesting penalty on all of these blocks that become else ifs. And so drop about 7 points there. Now that only gets us down to 20 out of the 27. But I think that's probably the best we can do for this method. And the point here is not to make arbitrary changes just to game the numbers. We really are after making this an easier read. So the next one I want to look at, we're at 24 on this one. And I think it's easy to see that the complexity here comes from the nesting. The nesting makes this hard to read. So the obvious target is to get rid of the nesting. And we could very easily address this by pulling out a separate method. And probably the sweet spot for that is this if. So if we were to move this out into another method, the nesting penalty drops off of almost all of this because it goes to the top level of the new method. All right. So that's one way to fix this. But I just want to point out that we've also got here an if with nothing in it but another if, with nothing in it but another if. So if we were to combine those three ifs, that's going to add a sequence of logical operators when we AND those conditions together. That's +1. But then we drop the nesting of everything inside by 2 levels. That's going to drop us a lot of points, make the method a lot easier to understand. 30 versus 15. And what I get for running through this right before and not making sure to reset everything. If I look at where the points are coming from, got some +3s. It's not terribly deep. So again, we've got the option of extracting to another method. But another thing that I noticed when I was looking at this code was that over and over and over again, we do this string not null and string not empty. So we do that here. Every time we do that test, we've got an increment for the logical operator. So if we were to pull that out into a helper method, that's going to make this code more readable because instead of reading both conditions every time, what I'm going to be reading is something like, if string is not empty with an argument of query, do the stuff, right? So that's going to make the code easier to understand. Now, just as a note, we're in the landmark shops application here on SonarQube.com. We'll see this again in a minute. This one is also from Landmark Shops. We're again doing this string not null and string not empty, not null and string not empty. So if they were to pull out that utility method, make it available across the project, of course that's going to help everywhere. The other thing that we can do here is so that's one of the things that we can do here. The other thing is that really if you just step back and look at this method, there's a lot going on here. We're asking a lot of the maintainer with this. And so structurally, I don't know that I would necessarily make a lot of changes, but probably what I would do is pull it off into another method. An evocatively named method here would help a lot when you have to understand what this method does. Or failing that, like that block off into another method. Okay, so I'll skip that one. Yeah, that's okay. I can skip that one. Although that was a really good example. Okay, so for this one, we're at 72 versus 15. And so let's just take a look at what's in this. Notice that we've switched to C# here. So I've got a switch and a case with a lot of logic, and then I've got another case with a lot of logic, and then the default, and it's over. So this method consists of two cases. 100 lines. So I think this is an obvious candidate for offloading the contents of a case in particular into another method. In addition to making this easier to understand, we're going to drop the nesting increment because all that logic comes out of the switch. I'm at 17 versus 15, so that's not terrible. If I look at where the points are coming from, I've got not a lot of nesting. It's really just coming from the volume of stuff. Again, we're only at 17, so I don't know that there's a lot that I would really do with this. In fact, if this were my code and I were just looking at the top half of this, I would probably say, you know what, I'll just take those 2 points and move on. But then I notice that down here at the bottom, I've got these catch statements. And for each type of exception, I'm doing exactly the same actions. Now, since Java 8, you can catch multiple exception types at one time. So if I were to combine those exception types, of course it makes the code clearer, and it drops me the increment for each of those extra catches, which gives me 4 points, gets me below the threshold. Now, you might have noticed that the interface just changed slightly. We've jumped to next.sonarcube.com, which is where we dog food the changes that are coming in the next version. And one of the changes that we'll see in the 6.4 version is this extra panel here at the bottom to pull out and make it easier to deal with the secondary locations. So if I look at this method, I'm at 40 versus 15. And eyebrows raised, that's kind of high. So let's look at it. I'm in an if-else-if structure already, so there's nothing to do there. Not any nesting. Nothing I can do there. Really long method. But just looking at it, I notice all of these uppercase values here. And I think this is an enum. We'll turn this into a switch over an enum, which is easier to understand and drops me all those points. But then I started looking more deeply into the code and I realized this is not an enum, that what we're actually doing here is sort of a complicated type check, basically. They've written some helper methods around type checking, but that's what's going on here is type checking. And so what I come to with this method is that there isn't anything that I can do easily to refactor this, that this is just part of the essential, the core complexity that's required to get the job done. And of course, you know, we all know that in any program, there's a minimum amount of complexity required to get the job done. If I did really want to get rid of this complexity, it would have to be a far deeper refactoring to perhaps introduce that enum that I thought I was looking at. And whether or not that's worth it is not my call because this is not my application. And I'm showing you this to make the point that I don't think cognitive complexity is panacea. There are some times when you just have to say, this is as good as we can do and walk away. But cognitive complexity can certainly help you find the places where you might want to take a second look. Probably noticed that that was my last tab. So now I'm going to go back to the slides. Okay, so we've looked at refactoring, and I hope I didn't go too fast. I hope that made sense to everyone. Just briefly, as a recap, cyclomatic complexity is the measure that most people think of when they think of measuring the complexity of code, and it does measure the number of test cases, the minimum number of test cases you need, but it doesn't give you a good relative measure of understandability. Cognitive complexity, hopefully, does that by incrementing for breaks in the linear flow, incrementing for nesting of break structures, and by ignoring readable shorthand. Now, I just want to mention there is an increment in cognitive complexity for the ternary operator, which is a shorthand code structure. But I think most people would agree that typically used, it's not a readable shorthand structure, which is why we don't ignore it. High cognitive complexity is something that tells you, hey, you need to look at this for refactoring. Maybe you can't do anything about it, but a lot of times you can. The refactoring patterns that I showed you were early return, moving nested ifs up to be an else if, chaining sequential ifs, pulling out helper methods. So when you're doing the same thing over and over in code, pull that out, centralize it in one spot so that when you need to update it, you update it once, it updates everywhere. Combining the catches, which unfortunately is only available in Java. And of course, the go-to, extracting nested complexity into another method. That's all I've got. Are there questions, or are you too busy with the pizza? Sure. That's a great question. Thank you. Okay, so the two questions were, is this just for the languages that I looked at explicitly, and is this software free? So first, it's not just for Java, C#, and PHP. Those are the three languages that we looked at today. I was very careful to write this language agnostic. So just like cyclomatic complexity talks about the basic structures of programming, that's what cognitive complexity is also concerned with. To date, we've implemented a cognitive complexity rule for Java, JavaScript, PHP. Member implemented it for Perl, C#, the C family of languages, so C, C++. And we're planning to address this also in COBOL, RPG, ABAP. I don't know if this is appropriate for PL SQL and PL1, but we're going to look at it. Basically, anything that has logical structures, this would apply to. Now, as to the question of whether or not this is free, SonarQube itself is free and open source, has been since 2007, and the vast majority of analyzers are also free. So Sonar Java, Sonar JS, Sonar PHP, et cetera, et cetera. The legacy languages are commercial, so C family, COBOL, ABAP, RPG, Swift, but I think we're going to open source that this year. And of course, Swift is not a legacy language, but for most people, this is available for you today as a free download. And thank you for asking that. I didn't want to get into, we're free and open source, come try us, because I'm not here to pimp my products, but thank you for the opportunity. What else?
Control flow, like variables or class structures such as inheritance and how they affect complexity?
That's a great question. So cognitive complexity is concerned only with control flow within a method. And we will be adding class level and higher metrics later this year. But for things like global variables, that sort of thing, it doesn't address that. We are kicking around internally having another metric that would address some of those higher level concerns. But the thinking on that is very, very, very early, so I can't tell you any more than, yeah, we've thought about doing something. And I saw another hand back here. Yes,
Right
sir.
here. Just curious what feedback you've gotten from folks that have adopted cognitive complexity. Just kind of curious.
So the first feedback we always get at SonarSource is the internal feedback, and we don't pull punches internally. And generally, it's been pretty good. We did adjust what the metric is based on early internal feedback. For instance, in the first iteration of this, there was a nesting increment for else, if, and else. And what we found was that the number just racked up too quickly. And so that's why there's no nesting increment now for else and else if. We've gotten a little bit of feedback from the community. Honestly, not as much as I'd like. I have had some people say, you know, wow, this is great, I'm really excited about it, and then I don't hear any more about it. And to be honest, that's typically the folks that love most of what we do. So I don't know that I've had a lot of gloves off feedback yet, and I would love to get that. Who else? All right, so, oh.
How new is the cognitive complexity measure?
So we published the white paper in December. So 3 months now? Okay, so that appears to be all the questions for now. If you have questions later, you can reach me or my colleagues on Twitter. And there's also a SonarQube Google group that I respond to almost every day. So, thank you.
Thanks, Anne. Appreciate that. Again, if you're with us during our regular programming, we're not normally this chaotic with the pizza and whatnot. So sorry about that. On your way out, I think there's plenty left, so please grab some if you didn't get your fill. Otherwise, we'll see you all next week for Klaus's talk.